two matrices, and so how do you compute the eigenvalues then? So remember, if you have a square matrix A, you need to have a non-zero solution to this, right? This is the same thing as saying okay? So it means to say that you have a square matrix and the corresponding homogeneous equation has a non-zero solution. This can only be true if and only if this matrix is singular. Okay? And this is true, we know, if the determinant is self. So that last line gives you the clue how to compute this. Remember, what is this? Now, in this self-assessment for eigenvalues, the whole fact about computing determinants and so on is a prerequisite. I have given the links and in the appendices of material from pretty old books, but it seems that wait a minute, I have to stop this. Hello, Tabo. Yes, sir, there is from one of the places. There is a leakage coming out, or possibly there is some noise. Yes, please. Yes, please. Okay. So this gives you. Now, what I was saying was I have given you material for this determinant. You should, so computing determinants is something which should be you must be familiar with it. Okay? And obviously about computing determinants of block matrices. So that also I have given the references there, okay? So now, it turns out if you look into this is a polynomial. In lambda with coefficients being functions of the entries. In fact, not functions only, they are just polynomial functions. Being polynomials. therefore, this one is a real polynomial. Okay? And this is called, it's usually denoted by this chi a of lambda. This is called the characteristic polynomial. So what are the eigenvalues? When to compute the eigenvalues, it's now very simple. You look into the determinant of the a minus lambda I, which is the characteristic polynomial. Its real roots are the eigenvalues. Okay? And how do you find the eigenspaces? Well, you solve this. You solve this linear system of this homogeneous system of linear equations, which we know now how to solve. Yeah? You will Gauss-Jordan and so on and so forth. You know how to solve it. So that gives you your eigenvectors. Okay? For lambda. Okay? So
just a question. So that is the sign for chi matrix A of lambda.
yes. That is the usual signature symbol for this is the Greek letter chi.
I didn't know we use chi also in mathematics. I didn't know that we use chi also in linear algebra.
Yes.
I use it more often instead.
Yes. Okay? All right. Now, so now the whole question comes up. So, what is happening? What are the different possibilities? You have a characteristic. So, suppose A is of dimension n. So, you have a characteristic polynomial of degree n. Okay? It may or may not Now let me stop for a while and say why Axler in his book takes complex, and that is the fundamental theorem. You know, if we had our scalars to be complex numbers instead of reals, okay, then just as we saw, like this, it will be a polynomial with complex coefficients, and the fundamental theorem says it always has roots. Okay? So, this situation doesn't arise in the case of Axler. Okay? This is a peculiar, reals pose much more problems. Complex gets much more easier. Okay? Alright. Over here there are also two more further cases. May have all real roots. May have some okay? But then it seems that the cases go on. Why? There's still another case. So you see, we saw a situation like x squared plus 1. I showed you. I left you. Okay? If you take this polynomial, if you take this matrix, its det minus its characteristic polynomial is exactly this. Right? So, its characteristic polynomial is exactly that. So, the characteristic polynomial may not have any real root at all. So, that's one kind of a thing. It has some real roots and some not. So, if it has some real roots, each of those real roots gives me some eigenvalues. Okay? And then remember, each eigenvalue gives me a certain number of vectors, which are its eigenvectors, right? So obviously, the question is, what is its dimension? Right? The next one that comes is, if it has real roots, it may have some complex roots, some real, or it may have all its roots reals. Okay? And further in this case, there are two extreme situations, and that I am going to say now. So that's where I am coming now. What is it? The first thing that helps us over here is this observation. Eigenvalues sorry. If or let me write it in words first. Eigenvectors eigenvectors corresponding to distinct eigenvalues are linearly independent. Okay? So let's try and prove this. So proof. Okay? So these are the eigenvalues. Vi is the eigenvalue corresponding to Vi is the eigenvector corresponding to lambda I. Okay? Now, suppose Now I'll do something by which I will show that alpha 1 is 0. What will I do? Take So it's a product, right? It's a product. Only the one for
Is that a composition?
Yes. Remember, in our home, the product is actually compositions, right? So this is a member again. Yeah. Now let's apply it on this side. Okay? Let's see what will happen on this.
Just a question. Are we not supposed to also have lambda 1?
Ah, good. So I just removed it.
Oh, so you replaced it with a T1. Oh, I see.
Okay? No. I took T1 to be this product where I've just taken out the corresponding thing for lambda 1. If I now apply it to this equation star, what will be T1 of this? T1 of V1, I don't know, but T1 of V2 must be 0 because this one vanishes, right? T1 of V3 must be 0. Okay? So if I apply, therefore, T1 of V1, let's see. Well, it is T of V1 minus lambda 2 of V1, that is not 0. None of them is 0, right? It can, wait, not only that. Something is important. Something is important is that T minus lambda 2 this cannot be 0, right? First thing. Why? If this was 0, then you would have T of V1 is equal to lambda 2 of V1. That means V1 would also be an eigenspace, will belong to the eigenspace for lambda 2.
So you're saying V1 will be eigenspace for lambda 2?
See, when you say that lambda 1 is not equal to lambda 2, yeah? Okay. So what I'm trying to say is T of V1, suppose it was this. So what does it mean? This means that V1 is non-zero, right? Right? Yes? So this means that V1 is an eigenvector for lambda 2. Right? Eigenvector corresponding to lambda 2. right? But you told me V2, V1 is the eigenvector for lambda 1, and lambda 1 and lambda 2 are distinct. Yes? So it cannot be that V1 is also in that eigenspace. Right? The eigenspaces, they actually meet only at 0. You cannot have anything common. Right? Can you get this? Yeah. So therefore, when you have this, T1 of V2, so T1 of V2 is 0, because this one is 0. T1 of V3 is 0. T1 of so on is 0. But you have something like this. Okay? Right? Now let's see what is T1. So this is a vector and this is a scalar. So this means that alpha 1 is equal to 0, or T1 of V1 is equal to 0. But T1 of V1 is equal to 0 means V1 is an eigenvector of corresponding to lambda 2 or lambda 3 or lambda k, right? So this is never true. So therefore, alpha 1 is equal to 0. Okay?
So we're going to leave the T1 of V1 once we equals to 0.
Because if it were 0, if this was 0, from the definition of T1, V1 would have become an eigenvector corresponding to lambda 2 or lambda 3 or etc., right? But it is not, because it is an eigenvector corresponding to lambda 1, and lambda 1 is distinct from each one of them, is not same as lambda 2 or lambda 3 and so on. So an eigenvector of corresponding to lambda 1 cannot be an eigenvector corresponding to lambda 2, right? I think you didn't get this.
I think I have to go back and redo.
Yeah. Again. So the whole point is, what I'm trying to say is, if lambda and mu are two distinct eigenvalues, T of V is lambda of V, and this is same as mu of V, would imply that V is equal to 0. Okay? That is what I'm trying to say. It's very simple. See, if V is an eigenvector for both lambda and mu, then you have this. So lambda minus mu times V is 0. But you have told me that it is an eigenvector, so it's non-zero. So lambda must be equal to mu, therefore.
So sir?
Yeah.
A non-zero V can't have two distinct eigenvalues.
Correct.
Okay.
Correct. Essentially, what is this saying is lambda the eigenspace of lambda and the eigenspace of mu, they just meet at 0.
So the only common at 0.
Yes, because they're subspaces. They're only common at 0, nothing else. Okay? Yes, this is a very, very important property. Okay? So therefore, it turns out that T1 of V1 cannot be 0. Okay? And therefore, it must be that alpha 1 is 0. Now what was the trick that I did? I found out a suitable linear transformation made out of these. To show alpha 1, I have just thrown out T minus lambda 1. So to show alpha 2, I just throw out this lambda 2, right?
So that they're all different.
Correct. Yeah. So therefore, similarly, shows therefore that eigenvalues, eigenvectors, so different eigenspaces therefore are, well, they are separate, right? So what's the scenario? The scenario is this. So if you tell me that lambda 1, lambda 2, lambda n, let me say lambda k, I don't know. So because I had v, its dimension is n, I have p, and suppose you tell me that lambda 1, lambda 2, lambda k are its eigenvalues. Okay? So now I have already seen, therefore, what's happening? Right? So now, if I take a sum, so my question is,
another question, sir. Why can I be equal to j?
yes, but if I is equal to j, they will be same.
Oh.
So what I am trying to say is the eigenspaces. Okay, so if this was your v, what I am trying to say is here is a kind of a thing. So this is okay. It's a kind of a decomposition, right? So this is possibly if k is 4, it's something like this. What about the rest? Okay? So this is what we are getting, right? So that's what I'm trying to say. So this one, we can take this. Okay? But remember, since they are mutually disjoint in this sense, this sum is actually unique. Right? But this is a subspace of V. Yeah? The question is this same as V? So this is the real question. Yeah? This is the real question. If it were, let's see, suppose what happens if it were. If it were, then What do I mean by this? Well, this is our basis for this spans. Okay, so it's the dimension of this is T1, see? If the answer is yes, the dimension would be therefore dimension of this one plus the dimension of this one plus the dimension of this one.
Oh, separated.
Yes, right? So this part spans so you'll have it will be possible to have a basis of V consisting of eigenvectors of T, okay? One part, each part, well, I've kept it in this way. So it will be possible to get hold of a basis. If this is true, it shall be possible to get hold of a basis whose basis vectors, there are parts, it can be partitioned, each partition spanning each eigenspace, right? Let's see furthermore what happens. What would be the matrix? What would be the matrix of T then? The matrix of T with respect to from V to V, it will be a block matrix, right? So it will be something like this, a block of identity, something over here, right? The rest are zeros, okay? So this is one block, this is another block, the rest are zeros, I didn't draw the rest. The rest are zeros, okay? This is a T1 by T1 part, which is coming from this. This is the T1 to T1, T2 to T2 part coming from this. Yeah? Okay? Okay, so this would be the picture. So that it will be so the matrix representation of T would be kind of a block kind of a thing.
So basically a structure of an identity.
Kind of, but with the ones being replaced by square matrices. Yeah? Clear? And the rest are all zeros over here. So these zeros means they are zero matrices. Okay? So that would be the picture, very natural. Because whatever basis, other basis we have taken on the other side, you would be taking the coordinates under this of that vector here. So that would give you this part of the basis, right? This would give you this part of the basis and so on. Yeah? Okay. So it seems that it's a peculiar situation. If you have no eigenvalues, it is not possible. So what does it mean that it doesn't have any eigenvalues? Well, it means that V cannot be decomposed by T in any good way. Okay? See, why good way? Why am I saying it's a good way? See what is happening over here. On this subspace, how does T look like? T is just taking multiple by lambda 1. Right? On the eigenspace of lambda 2, how does it look like? It is just taking multiple by lambda 2. Right? So you see, when I'm saying this, so do you see therefore that in each one of these eigenspaces, the linear transformation T is very well behaved. Okay? It's very well behaved because what does it mean? It means it is just being multiplied by lambda 1. If it is the eigenspace of lambda 1. Yeah? So, in case when T doesn't have any eigenvalue at all, it just means to say it is never possible to have the vector space V being decomposed into smaller parts where T kind of is just multiplying, is just scalar multiplication. Okay? It's never possible. But suppose if it has some eigenvalues, then we can say on some such spaces it is like that, but not on everything. So, this part which still remains open, okay? Over here T could be as wild as anything, as its formula says. Okay? The question that I am asking is, it may not be that T is just a scalar multiple, but whether on several subparts can I find subparts of it where it is actually some scalar multiple. That's exactly this equation, right? When can it happen? So naturally the question is, when can I have such nice decompositions? Okay? Furthermore, there comes in two more things. Remember, lambda 1 is an eigenvalue. That means it is it's a root of a polynomial. Now the root of a polynomial appears in several, it might be a single root, it might be a multiple root. Okay? So what do I believe you know what's a multiple root. So let's recall. Rather, if I can say it immediately, Px and Qa. So it's another polynomial says that. Okay, we also say this by saying alternatively okay. Now suppose I give you a multiple root. Obviously, you know, since it cannot, the number of times this factor can go inside Px cannot exceed its degree. So there is a largest thing, right? So the largest number these eigenvalues can come with several multiplicities. Okay? So if you tell me that lambda 1, lambda 2, lambda k are the only eigenvalues of a polynomial of an n-dimensional matrix, then it means that the multiplicities m1, m2, mk, okay, their sum must always be n. Okay? So that's one side. So let be eigenvalues . One minute. Oh, okay. Okay. So the sum of the algebraic multiplicities is always n. Now the dimension this is called the geometric multiplicities. Right? And the next result tells us the connection between them.
Sorry.
Yes?
Can you go back to the previous display? I was busy writing something there. Thank you.
Sorry, this will be geometric multiplicity of lambda. Okay? It's clear? Okay, so now coming back, so the geometric multiplicity okay? So this is the equation. So the geometric multiplicity is diverse, and the proof is, so we do it via matrices. So let and lambda eigenvalue of T with in K it cannot be 0 because it is an eigenvalue. It has a non-zero vector there. So it's at least one dimensional and it is at most n. Okay? Now take a basis. Okay? So now let's look into the matrix. So the matrix of T what will it be looking like? Well, it is coordinates okay? So, what is TV1? Remember, up to K. Up to K, you know TV1 V1 is an eigenvector of lambda. So this is lambda times V1. And so on up to TVK. Okay? So what does it look like? So this looks like lambda times V1, lambda times V2, and then something else. So what is this? I'm sorry, this is coordinates of lambda times V1. So this one, the first column would be lambda and the rest would be zeros. The second column would be 0 lambda, okay, and so on. The kth column would be, so in the kth place you are going to have this. The rest over here are all zeros. So essentially you see that this matrix looks like this. Okay, V is there. So let's take something else. Say P is not here. Say P and Q for some suitable matrices. P, this is its order is, so it has k rows, n minus k columns, and Q is a square matrix of order n minus k. Okay? So this is your, let me give this a name. So now let's find out the characteristic polynomial of this. So
he moved so fast.
Ask him to go back.
So fast.
okay? See, to find this matrix is the real issue. Once you find this matrix, the rest is simple. Okay? So, this is sorry. This shouldn't be a lambda here. Yes. And hence, and that proves it. Okay? K was our geometric. So that shows that the geometric multiplicity is always less than or equal to the algebraic multiplicity of eigenvalue. So what happens, so coming back to this tells us if the algebraic multiplicities are all smaller, strictly smaller, we cannot have in any way a full representation. So therefore, herein comes that, so thus, let me write this in a better way.